Physics reaction video number 58. Apparently energy and momentum, maybe just a one worked example. It's actually pretty short, so we'll surely be able to do the whole thing here. Here we go.
Okay, so here is example number 2. So this would be an inelastic collision. Okay, a 3,000 kilogram truck traveling at 50 kilometers per hour. You're welcome. I made it 13.9 meters per second for you. Strikes a stationary 1,000 kilogram car, locking the two vehicles together. Okay. What is the final velocity of the two vehicles, and how much of the initial kinetic energy is so-called lost in the collision? Okay.
So it sounds like there's a handout or a book problem or something where they can see the description of the problem. She read it to them, but looks like she's already sort of converted it to kilometers or meters per second. 3,000 kilogram truck. So it's like a 3-ton truck. Okay, so all right. And I think, did she say 50 miles an hour? Okay, so this is big. All right, here we go.
Right. Usually we shouldn't say lost. We should say dissipated or transferred out or something, right? But most problems still kind of say lost, okay? All right, so let's look at before and after, okay? And in theory, you don't...
So when I first started using pen tablets and styluses, so this is like 2005 or something, I was really intrigued by pressure sensitivity, and I used to sort of choose software based on pressure sensitivity. You can see that this has this, right? So these lines that she's drawn get thicker as she goes, and definitely for handwriting, it looks a lot better. It's interesting, kind of depends what you're doing. Definitely for handwriting, no question. So like equations and things like that, pressure sensitivity makes a big difference. But it's really interesting as you think about like how to set it, because by the end of this line, this gets really fat. And if she was doing handwriting, the fatness here could actually obscure some of the letters. And so I don't know, it catches my eye. But let's look and see how useful it is and contemplate what it would have looked like if she hadn't had pressure sensitivity here.
Really even have to convert the units for these, right? Because all the units are the same, but unless you're in a super time crunch, I would just always use meters per second. Okay, so that guy's 13.9 meters per second. That guy starts at rest.
Cool.
Okay, that was convenient. Okay, and then after, right, the cars are going to be locked together. Okay, so I don't know why they show it like this in the picture, because come on, that car, well, I guess it maybe could have flipped up there. Who knows? Okay, final. All right. Okay, so we want to set up our...
So it sounds like, she doesn't have total control over what this problem is. She said they, maybe that's from the textbook or something. Yeah, this is a crazy way to draw that, right? I think that's much more interesting. From my perspective, it's much more interesting to show it crunched, right? Some sort of little crunch factor, because the crunch really drives home the fact that something happened to the energy, right? Momentum's going to be fine, but energy is going to be lost, right? Like she said, dissipated or something. So again, notice how fat this gets at the end. So this is really, really interesting. By the way, there is some fake pressure sensitivity that has to do with speed. I don't think that's what's going on here, but maybe the faster you write, the thicker it goes, or maybe it's the slower. I'm not sure. I think this is true pressure sensitivity that she's using here. I think this is an iPad, but it's not 100% clear to me. Okay, so 13.9 meters per second, it comes at rest, and then it smashes into it, and then how fast is it going at the end? So it looks like a straight-up momentum problem, but it'll be fun to calculate energy too, just to see just how much gets dissipated.
Our conservation of momentum, okay, so M truck, V truck initial, plus M car, V car initial, equals their combined mass after and their V final, okay, and that's 0. Okay, so in an inelastic collision, you don't have to do the simultaneous solve, right? Because everything because they have the same velocity afterwards, okay?
Boy, that's such an interesting point, right? So inelastic is easier because there's only one final velocity. So normally you say, okay, 1, 2, 3, 4 parameters in this problem, and I can probably only solve for one if I'm doing just momentum, right? If I only have one equation, if it's a one-dimensional problem, I only have one equation. So given Oh crap, both of these are unknown. Oh, but they're tied together. So it's really just one unknown. So we're in business. That's what she was saying. And I think that's so great to sort of drive that home. Inelastic, when you think about, oh, figure out where that energy went, it sounds complicated. Like, boy, there's a whole bunch of other mechanisms involved. Yep, it's complicated. But from a macroscopic, hey, how fast are things going? They're always the easier problems, right? If you have two different unknowns over here, woof, you need something else. Oh crap, we're gonna have to do kinetic energy. Or if you've got multiple dimensions, right, it gets really hard. But oh my God, hey, they stick together, easy. So it's interesting to sort of compare and contrast sort of the mindset of approaching these problems.
I mean, I guess there could be a situation where not, but okay, and then that's 1,000, so that's 4,000 kilograms times VF.
Okay, so 3 times as heavy, so 3,000 down to 1,000. Yeah, so this is 3 times as heavy as that one. So it smashes in. So I'm just trying not to do the math in my head. I'm just trying to use my gut here. So I think it's definitely going to slow down. It's going to be less than 13.9. So in real life, a big truck, pretty heavy truck, comes and hits my car. Smash. Yeah, you know what? I'm not thinking this thing goes that fast. Well, 50 miles an hour. This massive collision, and then just sort of trickles forward here. Like, where could you be standing to get your viral video of this? I'm pretty sure this is actually going to work out to be pretty fast. Like, mathematically, we can see what's going to happen here. This term has hardly changed, so this term doesn't have to go down by much. So if I think about the videos I've seen of trains hitting cars, yeah, the train just keeps on trucking. But a car in a car, 3,000 versus 1,000, big, huge collision, maybe comes off the ground, bam, and then ducka, 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 ducka. So what am I missing there, right? Is my intuition wrong? Do those things have other things going on? Like maybe the car's in park, right? Maybe I'm contemplating when it hits a parked car and like either the emergency brake is on or the it's in park so that the wheels are locked, right? This is assuming could be, could move quite easily if anybody gives it a nudge. So I think that's interesting. All right, so now I'll make my guess here. So 3/4 of 14 is, I don't know, 3/4 of 15, 3/4 of 12 is 9, it's a little bit, I'm going to say 10 meters per second.
Okay, boom. All right, so then the final velocity is going to be...
Question for you here, right? When you plunk this into the calculator, right? Do you do 3,000 divided by 4,000? Do you just do 3 divided by 4? Do you cancel these zeros? How do you do it? How do you tell your students to do it? Let's see if we can go back and count how many button pushes is on her calculator. It's going to be tough, so maybe I'll slow it down. So let's go back 5 seconds. And let's go over here and let's do the playback speed, half speed. And let's see if we can count the button clicks. This might be hard.
Velocity is going to be... I don't know why I just didn't put 0.75, 13.9... 10.4.
Okay, I think I counted in the teens, 15 or so button clicks. So let's say you pushed all the zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it sounds like she did all the zeros. Well, it also says to the divide button. Oh, and the multiply button. I think she hit all the zeros. But did you hear what she said? By the way, let me put this back to full speed so before we forget. Normal. By the way, I gotta tell you, if you're grading student videos, I grade all student videos at double speed because I have to. I've got too much to do, right? I double speed everything. And a couple of really interesting things. First of all, you got to just be focused. Make sure you don't have any distractors and you can focus. You'll do fine. Second of all, interestingly, they all sound more confident. They all sound smarter. You give them a lot more benefit of the doubt because it's like da 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 da. And I feel like that's in the students' benefits. Of course, I mean, am I really identifying the students that are really struggling? And that's a really great question. But man, I use this playback speed thing all the time. Canvas has it too if you've got Canvas Studio going. Hey, and I was right. Close enough. I said 10. So I think we're good to go. I'm just going to back her up just a little bit. There we go.
Just input 0.75, 13.9, 10.4. Okay, 10.4 meters per second. Okay, which is slower than the than the truck came in, which makes sense, right? The truck's not going to get faster after it hits another car. Okay?
Like
All right, so you can see
40 miles an hour.
inelastic's easier because I don't have to do a bunch of stuff. Okay, simultaneous and stuff. Okay, but I can still find my initial kinetic energy of the system, m car v car initial, which is 0 because it's not moving, right? So the initial energy in this system is 3,000 times 13.9 squared. Okay, 0.5 times 3,000 times 13.9 times 13.9 is 2898.15 joules.
All right. Now, see, here's where my intuition just loses me. So, 250,000 joules. How many Big Macs is that, right? So, gigantic sample. I used to eat the double Whopper with cheese and bacon when I was in high school. I worked at Burger King, and I had the metabolism. Well, not anymore, but and that I think I calculated was like 2,000 calories or something like that. Let's say 1,000 calories. 1,000 calories we know is actually a million regular calories, right? And then so this is. Wait, did I do that right? So this is 250,000, 250,000 joules. Huh. So from a food perspective, that's not a lot. Yeah, see, I don't know. Help me, you guys. How do you get the intuition for energy? You could say, well, it's enough energy to lift the truck. How high? Well, that's the same as just launching the truck. Well, that's the same answer as launching the truck at 50 miles an hour straight up, right? So you could do that. But you're sort of changing energy to being a height experience. Like how do you develop intuition about energy?
Okay, right, because only the truck has kinetic energy in the first place. Okay, afterwards, right, they have a combined mv squared. Okay, so that's 1/2, 4,000 kilograms for the whole thing, and they're now moving at 10.4.
That's speed.
Okay, times 10.4 squared. Don't forget to square.
1,000.
EF equals 216,320 joules. Okay, so you can see that there's some kind of energy so-called lost or dissipated in this situation. Okay, so it might ask how much, like in a absolute sense. Okay, 216,320. So in an absolute sense, right, the change in energy was negative 73,495. It was a loss.
So there's a couple of really interesting things. This negative sign and this down arrow technically are canceling each other, but my favorite is the down arrow, right? So there's definitely a loss. Boy, this intuition thing with joules, it's so funny how hard I have to work. I thought, let me put it in terms of gravitational potential energy. Let me think about it in terms of a Big Mac or a Whopper. It's so funny how even momentum units are hard, but the only thing we're good at is things like speed and mass. So anyways, really, really awesome work here. It looks like there's a little bit more. So she still has a minute and a half. Seems like the problem's done. Let's see what else she's up to.
Right? It may ask you like what percentage is lost or what percentage remains, or whatever. So I guess let's see if I did over 298. Oh, no. 289,815. 216 divided by 289,815. Okay, that's about 0.7.
It's interesting that her fives look like J's, right? So at first I thought, what? It's not 7,000 joules, but that's actually a 5. Same thing down here. but there's no question she would catch it. If she misinterpreted her own handwriting to be a jewel, she would have caught it right here. She'd be like, what? Because it would have been, 10 or something.
7.5. Okay, so that's about a 75% is there afterwards, so that's about a 25% loss.
Cool.
Okay, so it could ask you in terms of that or something. Okay, it could also ask you, right, like if for some reason you don't know like this initial or something, right, like you can't solve this side, they could give you the energies in terms of some kind of fraction. I think we had that in one of the web assigns before, right? So it might say like, the initial energy is not equal to the final energy. Maybe it lost 20% or something, right? So then only 0.8 of the initial would be available for the final, right? Or something like that, right? And then you might have to solve that out and then go back and solve that.
So I really, really like this they that she's referring to, like they might do it or it might do it, right? So whether it's an exam or WebAssign or something, and this idea of stuff like, hey, we just did this problem, awesome, but hey, we could turn this problem inside out, right? Like it could, as long as there's only one unknown, you're good to go. And this notion of adding in the energy, we had said before that if it's inelastic, you don't really need to do the energy. But yeah, this you could say, oh, well, hey, 20% of the energy is lost. Can you get yourself back to how fast it was going in the first place? That's just really, really interesting. Let's see if that's true. Let's say all you knew were the masses and that it's inelastic and this. Well, okay, so you wouldn't know any of the speeds. Yeah, you could do it, but it'd be tricky, right? So I love how she's sort of setting them up for, oh, you guys, there's a gajillion ways this could go. Let's look carefully at it. So that was really, really cool. All right, well, hey, good work here. I really liked the commentary about inelasticity. I thought that it was, very carefully scaffolded and worked down to get to the result, but sort of workmanlike, right? Like, okay, hey, come on, let's go. We got this. And then the stuff at the end was super cool, especially this idea of, hey, we could ask this question in different ways. Very, very, very cool. All right, everybody. Well, hey, have a great day. It's super, super cold here in Minnesota, so we're dealing. And remember, physics teachers are awesome.